Hi, so this is the next video on data classes. Part 1 is published in this channel, so it's linked below in the description. And of course, the whole notebook that I'm using here is completely available in the GitHub repo, also linked below. It's fully annotated, so if you don't want to watch a video, you can also just read basically the Jupyter notebook, which has everything I talk about in here, as well as some additional details. So in the last video, we looked at basic data classes, we looked at equality, hashability, mutability, and immutability, also known as freezing in the context of data classes. We looked at the default ordering that data classes was able to provide for us. We looked at serialization to dictionary and tuple types. We looked at the fields introspection. We looked at how we can add our own methods and properties to data classes. We looked at one approach to custom ordering, which is essentially just adding, the ordering ourselves to it. We also looked at keyword-only initializer arguments, and we also looked a little bit at the performance and resource utilization of data classes compared to named tuples. So let's continue from that point. So this is kind of where we left off with a very simple data class. We were using that circle. So I'm going to keep using the same one. So I'm going to import data class from the data classes module. I'm going to create a class with these fields, and I'm going to pass that through the data class decorator. So the first thing we're going to look at is something called the post-init special method. So the special method post-init in data classes can be used to essentially augment the normal init method, which, remember, is being generated, right, by the data class decorator itself. So we don't really have a way of modifying that init method. So what they've done is they said, well, after the init method has run, the last thing we're going to do is call another method, and this one, if you implement it, will execute it, and then you can do whatever other initialization you want to do for your class. And because the post-init method is an instance method, it has access to the instance data. So it has access to x, y, and radius in this particular case for the instance. So it's very simple to do. Let's go ahead and do a simple one. So again, I'm going to copy paste code just so we don't have to spend time typing. So here's my class circle D just as before, right? But now I'm defining this special function called dunder post-init. And I'm just going to print stuff here. I'm going to say post-init called, and I'm going to print the representation of my instance, right? That's being passed in. This is just a regular method. We saw we can add those things to data classes since they're just regular classes. So now if we say C equals circle D, watch what happens. You can see that post-init was called, and then it did this print out here of the wrapper of C. So essentially this allows us to extend the init method without having to modify the method itself. So that's nice, right? If you need to augment the init, you can do that using post-init. So now there are additional variables that can get passed to post-init, and they are what are called init-only variables. So these are variables that are passed to init. So if we decide to implement a custom init, that variable will show up as a parameter as well. So these init-only variables get passed to the init method, which in general is completely written by the data class, but they also get passed to the post-init method as well. Now, they do not get stored in the instance dictionary or the slots if we're using slots, and that's why it's called an init-only variable. It's essentially going to be a field that we define in the data class, but it's not going to end up being a field in the final resulting class. It's going to only be something that gets passed to the init and post-init methods. So they don't get stored in the instance dictionary or the slots. Post-init will not have access to those variables via self. They'll only be accessible through additional arguments in the post-init. So let's use that to maybe perform a translation of the circle's center point, where we just want to allow the user to specify some x and y translations, but we don't want to store the x and y translations themselves. We only want to store the final center point of the circle. So to create an init-only variable, we declare it just like we would any other field. And again, the order of definition will be reflected in the order in which init and post-init parameters are defined. So we might do something like this. Let's just say that, and let's say it's an int equal to 0. So if we were to do this, then these would be regular fields. The translate x, translate y would show up, right? So if I say from data classes import fields, then if I look at the fields of circle D now, you'll see that we have those translate x and translate y right over here. They're regular fields, and we would have access to them through the self in the post init. But I don't want those to be fields in my resulting data class. I really do not want that. What I want is I want to be able to pass that essentially to my post init. I want the post init to calculate the new x and y and then store that and then just basically forget about the translate x and y. So to do that, we have to annotate the field with a special type, right? Not int. We have a special type. So from data classes, we're going to import init var, which means this is an init-only variable. And it's a special type, and it's a generic type. Just like you have generic types, like for example, list, for example, is a type, but you can say, well, I have a list of integers, right? If you don't know about Python type hinting, I have a video in this channel also on Python type hinting that will explain all that stuff. So init var is a type and it's a generic, so we can actually say that we want an init var of type whatever it is we want. So once we've got that, we can now write our data class this way. We can say I want an init var and I want this to be an integer type. So this is how I'm typing it. I can still keep the default and everything. Now what's interesting is that in the post init, we have self just as before, but now we are going to receive two additional arguments. We're going to receive translate x and we're going to receive translate y over here. And it will be in that particular order, in the same order in which it was defined as, in the class variables when we define our class. And so what I'm going to do here, and I'm going to copy paste that code, is I'm going to just do a print. So I'm going to say I'm translating the center by some delta x, which is going to be that translate x, and some delta y. And this is, by the way, just how you can put Unicode characters inside a Python string. Again, I have a video on that. If you don't know what that is, it's on Unicode. And I'm actually going to now modify self.x. So now this is, remember, the init has happened. Self.x is whatever was passed into the init with a default of 0. Same thing with y, same thing with radius. But here now, I'm basically going to override in the post init. I'm going to say, well, no, actually, I want to set self.x to whatever it is currently. And I want to add on to it the translation factors, the translation deltas for both x and y. So when we do that, I can go ahead and create a circle class. So circle D, I'm using circle D for data class to differentiate from the normal circle class that we were using in the previous video. And let's say that I have a circle centered at 0, radius of 1, and I want to translate x by -1 and y by -2. So if we do this and look at what it is, you can see that the post init printed translating the center, right, by delta x is -1 and -2. And then the circle D wrapper shows us that x now is indeed gone from 0 to -1, from 0 to -2, and then the radius was still equal to 1. And you'll notice that we don't have anything else, right, in the wrapper. We do not have translate x and translate y. As we saw, they're no longer fields in the class. So if we look at fields of circle D, you can see that we no longer have those things in there. We still have x, y, and radius, and that's it. So that's how we can do these init Init-Only Variables by using this basically special type that's available in the Dataclasses module. Now this is probably a case where I would want to make translate x and translate y named arguments and force it by making it keyword only arguments. So I can of course always do this, right? Python allows you to specify anything you want using a named argument. So that's fine too. So that would work exactly the same way. Let me delete this, we don't need that. But if I want to force this kind of approach to declaring the circle D, then I can do that by marking this as keyword only. And we saw how to do that already, one way of doing it. So from data classes, we're going to import KW only. So we saw that in the last video. And all I'm going to do is just copy paste this code. And then over here, we're going to use a variable that's just called underscore because we don't care about it. And then we give it this special type. So you can see how Dataclasses is sometimes using type hints to provide special functionality in the data class. And so once it goes through the data class decorator, we're going to have now these as init-only variables, and they're also going to be keyword-only variables. So I'll still be able to create a circle this way, right? This will work just fine. But if I try and pass them as positionals, that is no longer going to be acceptable and we'll get an exception. And of course, they're not in the fields. And by the way, since we're using a dictionary to store the instance, state, right? Not slots. We do have a dictionary available on the class. You can see it contains X, Y, and radius. It doesn't contain the translate X and translate Y. So now the next kind of broad topic that we need to dive into is field level customizations. We've seen how to customize things by basically changing, providing parameters to the data class decorator. We saw a couple of ways where we can modify what's going on by using type hinting, special type hints. But we have even more refinements that we can do by using the default value that we assign to a field in the data class. And the data class decorator, remember, uses introspection. It can see these default values and based on that, decide to provide different functionality. And the way it does this is by assigning defaults as instances of the field class. So from data classes, we can import the field class, but I'm also going to import the field function. So the field class is essentially just a class that's in data classes. But the documentation says we should never instantiate field directly. If we want to instantiate an instance of this field class, we need to use the field function. So we'd have to use a field function, and you'll see that if you look at the type of that, even though the wrapper tells us, but you can see the type of what comes back from the field function is indeed a field class, a field instance. Okay, so let's do a gentle introduction to using field to do additional customizations to our class. So let's go back to kind of our very simple class, Circle D. And remember that if I have now an instance of Circle D, the representation by default uses every single field that we have in the class. So X, Y, and radius here. And maybe that's not what we want. Maybe we want to have a special representation where we don't include the X and Y, we only include the radius. So maybe we only include X and Y, but we exclude the radius. And of course, this can be useful in cases where maybe you have sensitive data that you have in your data class and you don't want that to come out in the wrapper. Or maybe you just have so many fields in your data class that putting that into the, the wrapper would just be unwieldy. And so you want to kind of limit that. So when you only want to see a subset, what can you do? Well, this is a regular class. So if we were using a regular class, how would we do it? Well, we'd write our own wrapper method, and we can certainly do that as well. This will override, right, the representation, and the data class decorator, when it sees that you've implemented wrapper, it's not going to replace it with its own. It will leave your wrapper as is. So we could do something like this. And again, just to save time, I'm going to copy paste that from the notebook. And so I'm just going to return that. And as you can see, I'm going to omit the center point. I'm only going to keep the radius. So now if I do a circle D instance and I look at the wrapper, you can see I only get radius equal to 1. So I was able to provide this customization by essentially overriding the wrapper myself. Well, that's one way of doing it. But another way is that Dataclasses allows us to do it slightly easier. So we go here, and what I'm going to do here is instead of saying int equals 0, I'm going to create an instance of this field class using the field lowercase f function. And one of the parameters is to say that the wrapper is false. And I'm going to do the same thing here. By default, the wrapper will be true. Basically, it's going to say, okay, well, if I don't specify a field with wrapper equals false as the default for x, then I will include that in the wrapper. So now, if I make an instance of circle D, and I am going to have to pass in the values here, because you'll notice that we no longer have a default value of like 0 and 0 like we had before. We've got this field thing here. So we'll come back to that in a sec, but essentially we kind of broke the default, values that we had. So I have to specify the values now. But when I do that, it creates the circle instance, and you can see the wrapper now only includes the radius. So this is a way in which Dataclasses allows us to further tweak the behavior of the generated class or the modified class, because Dataclass just modifies this class. So we can change that behavior using this field. So we need to get back, however, to having a default. Well, that's again very simple, because one of the arguments that you can pass to field is default. So we can say, hey, use a default of 0. And here, use a default of 0. And I'm using named arguments, which means the order in which we present those arguments or we pass those arguments doesn't matter. So now if we do this, I can say C equals circle D. I no longer need to pass everything because now I have defaults for everything. And so you can see we get that. And of course, C.x and C.y should have defaulted to 0. And indeed, they have. Okay, so the next thing I want to look at are non-initialized fields. Just now, we saw how we can create these pseudo fields that are not fields at the end of the day, right? They're not attributes in the class data, but they still end up as arguments to the init and the post init, those init-only variables, right? We just saw that. But what about the reverse? Do we want to be able to define a field in a class, but we don't want to pass it as an argument to init? That happens as well. So this could very well apply to, let's say, calculated fields, where maybe we want the area in our circle, but we don't want to pass it. So I want it as a field, right, in my class, but I don't want to pass the area in the init. I want to have the init calculate the area and store it, and then I can access it like a regular attribute. So we can go ahead and do that. And we're just going to use plain properties first. So we're going to kind of fall back to using plain Python, not the functionality of the data class decorator. So you'll notice I still only have 3 fields in this data class, but then in the post init, I'm going to create a new variable. I'm going to make it a pseudo private variable called underscore area, and I'll make it pi r squared. And then I'm going to have a read-only property that's going to basically return that value whenever I ask for the area. So this is a mutable class. It's not frozen, which means I'm allowed to add underscore area to the instance. That's important. If I was to make this data class here frozen equals true, this wouldn't work anymore, right? So it's important here to realize that. So now I have this class, and I can say C equals circle D. So we'll make an instance. So remember, it's got a radius of 1, right? C is a radius of 1. And now I have the area property, 3.1415. And where did it get it? Well, it got it because the post init did this. Basically, it cached the area, and then it returns it over here. Now, there's a few things, right, with this approach that we need to think about. The area attribute is a regular property, and it doesn't show up in the fields of the data class. If I look at the fields of C or the circle D, whichever one you want to use, you'll see that we have X, Y, and radius, but we don't have the area. So from an introspection perspective, we've lost the fact that area is available. We also have an extra backing variable called underscore area. That's now in the class state. If we look at the c.dict, you'll see that we now have this underscore area in our class state. And of course, as I mentioned, if the data class is frozen, then trying to store a piece of data in self._area isn't going to work because it's not defined as a field in here. So I cannot do that. First of all, that would be creating a new, adding a new attribute to the class. We can't, it's frozen. And even if it was an attribute, we still can't modify it because it is frozen, or at least not directly. So if we want to keep things cleaner and more consistent, what we really need is a field that is defined in the class, but that is not expected as an argument to the init, right? So let's start there, and we'll worry about mutability later. So what I'm going to do is I'm going to take this over here. Let's paste it down. Let's remove what we don't need. We don't need to do the import again, and I don't want this property over here. What I'm going to do is I'm going to define an area, because I want this basically as a field in my data class. So I'm going to define it, area, and the type is going to be a float. But now I'm going to use this field function, and I'm going to create a field object, and I'm going to say that the init equals false. That is going to basically say this is a field in this class, but it does not get passed to init. So it is not required when we create an instance of circle D to pass in the area. That's what this init equals false does. It's essentially writing the init method without the area parameter. The other thing too that I'm going to do is I'm going to leave it out of the wrapper. I don't want it in the wrapper either. I'm not interested in that, so I'll take it out. And then in the post init, well, I don't have to do underscore area anymore because area is an actual, real attribute in my class. So I can just do it this way. So now we can create an instance of circle D. So we did that. We can look at the dictionary and you'll see that area is in here. So that's great. We know that we can, of course, retrieve the area this way, right? Not a problem. And also it shows up in the introspection in the fields. You can see that we now have area as well. Now we can choose to freeze the class if we want to. The caveat is that when you freeze the class, you cannot do assignments to an instance variable. Even inside the post init, that's just not going to work. So if we were to try this, let's take this class as is. And let's paste it down here. And here I'm going to say frozen equals true. Okay, so that compiles. And now let's say C equals circle D. And you can see that we get this frozen instance error exception. We cannot assign to the field area. That's happening in the post init. Now remember what I was telling you, how data classes implement, immutability. They basically override the setAttr method and they check basically in the setAttr of the data class, basically of this class that's been created by the data class decorator or been modified by the data class decorator. The setAttr method has been implemented and it checks to see if the name that we're trying to change, so here, area, is that one of the fields of the class. If it is, and the class is frozen, then it's going to raise this exception. Otherwise, it will let it happen. It will let it go through. And that's how the setAttr method is defined on this class, on the circle D class. That's very important to realize because if I want to circumvent that, right, what I want to do now is I still want to have a frozen class, but I still want to be able to have this field with init false, and I still want to be able to populate it with this value over here. I need to circumvent what the data class is doing. Now again, this is something where we're starting to fight the data class, and I think it's still okay though, because the fix is actually very straightforward. So let's do this. What I need to do is, this is using the self.setAttr, right? Essentially, this is what it's using. It's saying set attribute, and we're going to set the attribute called area, and let's say area, and I want it to be pi times self times radius 2. Okay, essentially that's what we're doing here when I had the code before. Now this isn't going to work, right? C equals circle D. That's not going to work. I get this frozen error, cannot assign to field area, right? So what I want to do is I want to bypass the set attribute. I don't want the one that's in my circle D class. I want the one that's above it in the object class, because that one doesn't have that limitation. So all I need to do is call the setAttr method from the superclass this way. So now when I do this, I'm no longer using the set attribute of the circle D class, and I can now create an instance of my circle D class. And if we look at the area, that's been properly populated, right? If we look at that, but it is still an immutable class. If I say c dot, let's say area equals 10, that's going to fail. If I try and say c dot x equals 10, that's going to fail. It's still frozen by the rest of the code that was added to my circle D class by the data class decorator. So we could even start using this type of thing using super and the setAttr to maybe do like lazy evaluation of properties in the data class, right? But I think at this point, once you start seeing this kind of thing too much in your data class, I would step back from using a data class and go back to just using a regular Python class. Now at this point, you're starting to fight the data class. That's not good. Okay, so let's continue looking at what we can do with this field, right, in the initializer, in the default value, I should say, of the class. So we know that we have two types of comparisons to deal with. We have the dunder EQ for the equality, and then we have the other ordering operators like less than, less or equal to, etc. Now we looked at this in the previous video and saw that equality and default sort order is based on the tuple comprised of all the fields in order of the data class. So let's start with a mutable data class to avoid the additional complexity of hashing, because I just want to focus on the ordering right now. So let's go back to our simplified data class. So just as a reminder, equality of two instances of the data class is based on the equality of the tuples containing the field values x, y, and radius, right? So if I say C1 equals circle D, and then we'll do 1, 1, 1, and then C2 is equal to, well, the same thing, like so. Then we'll get, of course, that C1 equals C2 because we have 1, 1, 1 equals 1, 1, 1 as a tuple. Now, by the way, init-var fields are not part of this tuple, right? We saw init-var fields, init-only variables. They're not basically fields in the class, so they're not going to be part of the tuple either. Now, we also saw how to add ordering to our data class. We could do something like this by just basically saying order equals true, like so. If I can type. So when we have that, we have C1 less than or equal to C2 is available, and of course that's true since they're actually equal. But what if we wanted the ordering to be based on the radius only? We looked in the previous example of how to do it based on the distance from the origin. We saw we basically had to write our own custom ordering function. Now, what you can do with data classes is you can actually specify which fields should be used in the comparison in the data class. So if we look at this, we could go ahead and say, well, I want my int now to be a field instance. So I'm going to create it. Of course, now I have to specify the default this way, but I'm going to compare false. So I'm going to say X should not be part of comparisons. Okay, so now I'm going to do the same thing here. Default equals 0 and compare equals false, like so. So now if I create, let's say C1 equals circle D, let's say 1, 0, 2, and then C2 equals circle D, let's say 1, 1, 1, then if we look at C1, let's say less than or equal to C2, well, the radius 2 is not less than or equal to 1. So we get that this is false. And if we were to look at the reverse, C1 greater than C2, that's true. C1 greater than or equal to C2, that's true. And that's because the data class now basically defined the ordering only based on radius, because that's the only one that was left. We said don't use X and don't use Y. The only caveat is that this also changed the way that the equality worked. So if we take a look at, let's do this. I'll make 2. I'll make C1 equal to that, C2 equal to that, but I'm going to change, let's say, the center point of C1. So now we have two circles of equal radius, but at different center points. If I look at C1 equal to C2, guess what? I get true. And if we were to make this frozen, then we would also have problems with the hashing because, well, it wouldn't be a problem, it would be correct. But because we've changed the equality, and then if we make it frozen, it will become hashable as well, this means that these two circles would actually compare and hash equal to each other. So if you're in a situation where you need different mechanisms for equality and ordering, as might be the case for the circle class, I want equality to be based on X, Y, and radius, but I want the ordering to only be based on the radius, or maybe only be based on the distance from the origin. Then you're going to have to provide your own mechanisms for equality and ordering. Once you start layering in the hashability, right, frozen equals true on your data classes, you're going to start having to fight things, and you're going to have to figure out, well, what's going on? What's defining the hash? What's the equality? How's that interacting with the data class decorator? I think at that point, again, you're probably going to be fighting your data class too much. So if you find yourself fighting data classes to make them do exactly what you want, that is kind of beyond the reasonable capabilities of data classes, I think you're barking up the wrong tree. You write custom classes by hand and just avoid the unnecessary complications of hacking the data classes code generator in some weird and wonderful way, which only you can understand and nobody else reading your code will. And I've seen that, and I think that's the wrong approach. I think at that point, don't use a data class, just use a regular class, right? Data classes do not replace classes. It's just a code generator that helps you avoid writing boilerplate code. But if that starts making you writing more and more complex code just to get around it, just to work your way around the limitations, you'll just, that's just the wrong approach. Anyways, I'll get off my soapbox. So let's go back to hashing. Right? So we've covered a lot of ground on hashing in the previous video. So to refresh our memory, here's what we said last time. The instance state used to create a hash for the instance should be immutable. Now, this doesn't mean that the entire class should be immutable. What it does mean is that we should, in most cases, right? I'm sure there's exceptions, but in most cases, we should follow the following kind of simple rules. The instance data used to generate a hash for the instance should be immutable. We saw what happens if it's not. The same data used to generate the hash should be part of the equality implementation as well. Doesn't have to be, but generally it is. And then two instances that compare equal, and that's really important, should have the same hash. Again, I explained that in detail in part 3, I think, of the deep dive series. And you have all the Jupyter notebooks, available for free in GitHub. I have a link to that repo as well. Okay, so looking at this, let's just do a regular class and let's just try it out just so I can show you what I mean by this. So let's do this person class. So I'm going to have an init where I'm going to pass the name, the age, and the social security number. Now, the name can change over time. I don't have a problem with that. I don't have a problem with the age changing over time. I mean, it'd be nice if it didn't, but it does, right? So the age is definitely going to change over time. What I don't want to change over time, what I want to be immutable is the SSN. This in the US, we call that the social security number. It's basically a unique identifier. You can think of it as a unique identifier for people. So now I want my equality of two people to be based only on the SSN. I don't care about name and age. So I can write this EQ method that's going to, best practice, just make sure that we're comparing ourselves to another person instance. And if it is, only look at the SSN property. Otherwise, it's not implemented. And then for the hash, therefore, we're only going to hash the SSN. That's all we care about. So if you look at how we've done things here, well, the instance data used to generate a hash for the instance should be immutable. Well, that's not the case yet. SSN is mutable at this point. Okay? But the other ones are fine. They don't have to be immutable. Name and age are okay. The same data used to generate the hash should be part of the equality implementation. And that's kind of what we have. We hash the social security number, and we use the social security number for the equality as well. And then two instances that compare equal should have the same hash. Well, this is why we usually have, the second one over here is because, well, if two instances are equal, which means the social security is equal, they should have the same hash. That means I need to hash just the social security number. Okay? So if we do this, we're most of the way there. What we still need to add in, though, is basically just make the SSN immutable. So for that, I'm going to use a backing variable called self._SSN. And then over here, I'm going to add a property for SSN that's going to return that backing variable. And it's a read-only property. There's no setter defined. And then while I'm at it, I'm also going to create the wrapper. And you see what I did here? Bad me, right? I didn't use self.class.name.qualName with the double underscores and everything, right? So I just hard-coded this. As I said, I don't always follow what I preach. So I'm a bad person. All right, so now let's create some person instances. So we're going to create 3 people. And what I'm going to do is that person 1 and person 3 are going to have different names and ages, but they're going to have the same social, right? And then person 2, everything's going to be different. So when we do this, we can compare P1 equal to P2. We can compare P1 equal to P3. And as expected, P1 is not the same as P2 because the social security numbers are different. However, P1 and P3 do compare equal because they're true. And of course, the hashes, we're going to see a similar kind of pattern. If we look at the hash of those 3 things, you'll notice that the hash for P1 and P3 is identical. That's the way it should be because P1 is equal to P3. And of course, the hash of P2 is different. So now we can, of course, create a set with these 3 instances. We could say P1, P2, P3. And as expected, we only get 2 things in here, right? Because P3 is the same as P1. So the set, remember, removes, only keeps unique elements. So it basically ignored one of those. And then the same thing would happen for a dictionary. I could say D equals P1, person 1, and then we could say P2, we'll say this is person 2, like so, right? So if we have this dictionary here, okay, we have that as expected. Now, if we try and modify one of the instances in the keys, right? So we have this key P1 and P2. Things will still work just fine as long as we only modify name and age, right? So if we say, let's say P1.name equals X, and then P1.age equals 100, if we look at the dictionary again, that worked perfectly fine. It only touched this one here because that was P1 and it was okay. Remember, the only problem that we have is if we were to change the value that's used for the hash and the equality. Well, we're not, and in fact, we can't because we made that a read-only property. So if I were to try and change it to, let's say, 2, 3, 4, 5, 6, right, then I'm not allowed to do that. So now, given all this, we know that data classes will implement hashing for us if we make the data class immutable. So let's do this person class, but using a data class instead of typing all that code out. So what are we going to do? We're going to make the data class frozen. We're going to have name, age, and social. So at this point, the whole class is frozen, right? Everything is frozen. So we get, we've created P1 and P2. They're hashable. We can make a set out of these instances. We get that. We can do a dictionary. And equality is based, of course, on all the fields, right? So if I do this, let's say these, let's do this. So I've got the same social security number for all three. I've got person 1, that's A and 30, and person 2, that's A and 30. So P1 and P2 should be equal. P3 is the same social. You know, with the custom class that we did just now, I would actually consider P1, P2, and P3 to all be equal to each other. But with the data class, not so, because data class is going to use every field in there for equality and for the hashing. So if we look at P1 equal to P2, P2 equal to P3, and P1 equal to P3, you'll see that P1 equal to P2 is true because everything is the same. But P2 equal to P3 is false because A and B, right, 30 and 40, even though the SSN is the same. And then same thing with P1 and P3. So what we really want to do is to base the equality and the hashability on the social security number field only and let the name and age be mutable. And that's what we had in our custom class, right? The social security number was immutable, age and name were mutable, and the hash and the equality was only based on the social. So we want to try and do the same thing, but now using a data class. So we could start by limiting what fields are used for both equality and hashing. So let's go ahead and do that. So we'll create our frozen data class. We will put our name and say compare equals false. So now we're taking it out of the equality and therefore the hash as well, because now we have frozen equals true. So the data class is going to try and implement a hash function. Of course, you can always override that, but we're trying to use the default settings in the data class or the default functionality of the data class. Then we'll do the same thing for the age. So at this point now, we have an immutable and hashable class. So name, age, and SSN are all still immutable. And the SSN is going to be used and only the SSN is going to be used for equality and hashing. So if we create two instances of now the person class, you'll see that P1 is P2 is obviously false. They're not the same objects. However, from an equality perspective, they are the same. And also, of course, since they're equal, we would expect that the hash of each one of them is going to be equal as well. So as we noted just now, this of course would affect the default ordering. If we were to order, if we were to make the data class orderable using order equals true, right, in the decorator argument. Because now it would only order based on SSN. It wouldn't order on name and age anymore. Now, more importantly though, our data class is frozen. So even though we technically, from an equality and hashability perspective, should be able to mutate name and age without having any bad side effects, as we saw with the custom class that we used, we can't, right? If we try and say P1, right, P1 is this person over here, and say P1.name equals B, that's not going to be allowed because we have a frozen instance. So the first thing we need to is to unfreeze our data class, unless we want to start overriding the safeguards in the data class using this super set adder that we saw before. Maybe there's a way we can kind of, jam that in somewhere. But I really wouldn't recommend it. At this point, we're just finding the data class, and it's time to call it quits. But let's say that we're okay making the data class mutable again and relying on ourselves, and more importantly, other developers in our code base, not to modify the immutable attributes. So if we're okay taking that risk, right, and this is why it's called unsafe, what we can do, we can make a data class, and I am not going to set it as frozen now. So I'm going to leave it mutable. And I'm going to say class person. Actually, let me just copy paste that. So just like we had before, I'm not going to put name and age in the comparison, which means that for equality, it's only going to look at SSN. Now, the class is not hashable because it's not frozen. So if we do p equals person, let's say a and 10, and let's say that the SSN is 1, 2, 3, 4, 5. So if we do this, that's fine, but we can't hash p, right? As we saw that before, that unless you make the data class frozen, it's not hashable because that's the safer way of doing things. So what we can do, however, is we can say, no, I still want this thing to be hashable. Now, I could, of course, just go ahead and define the hash function here ourselves, right? We can do that. This is just a regular class. So we could say return self._self.ssn this way, right? So we could do that, and now it would be hashable. And of course, sorry, we need to return a hash, not a string. Okay, so we get this hash over here. The equality should have been implemented by the data class, so that's fine too. So essentially, this is how we can approach this. We can write our own custom hash and basically just hash the SSN. But what data classes allows us to do is to say, well, make unsafe hash equal to true. And when you do that, it essentially creates and generates this code for us. So we don't need to put it in anymore. We can just use it like that, and now it's hashable. Okay? So it creates a default hash function for us. And that default hash function is going to be based on SSN only, since we took out name and age from the comparison. And so this is why this is called unsafe, because now nothing here stops me from saying, well, p.ssn equals 23456. That's fine. Hey, I just mutated it, right? I just mutated the field that's used to create the hash and the equality. And as we saw in the last video, that's not good. It is, however, okay to change and mutate name and age. Okay, so moving on, let's look at the next thing, which is keyword-only arguments. Now, we already saw how we can separate arguments into positional and keyword-only sections in our data classes. Let me just remind you, this is what we did, right? We used this keyword-only data type to separate essentially the arguments that are going to be passed positionally to the init and the post-init, and the arguments that must be passed as named arguments to the post-init and the init. So we did that and we separated it. So that's one way of doing it. Now we have another way of doing it. So I'm going to take this class and we're going to modify this a little bit. I'm going to remove this altogether. And instead what I'm going to do, instead of making this equal to 0, we're going to use a field again. So we're going to say field. Now, of course, I have to specify my default. So we'll do this field default equals 0. And what I'm going to do is I'm just going to specify now another argument called kw_only equals true. And so the data class now sees this and says, oh, okay, well, these are keyword only arguments. And the way I've got it listed here is that it would be the same as what we had before when we had that kw_only type. The only difference is I'm using a field here. And what happens is that in Python, as you well know, if you've got a bunch of arguments to a function, then the name, the named only, the keyword only arguments must be defined in the function signature after the positional ones. So we could, however, build it this way. We could say, hey, let's go ahead and put this translate over here and change the order. That's still going to work fine, because if we look at the circle D init, you'll see the way that the data class has changed this init. It basically changed the order. It said, okay, X, Y, oh, translate is a keyword only, so that's going to have to go somewhere else later. We have radius, well, that's still positional. So it basically rewrote the order as X, Y, radius, and then it put translate X, which was the first one, and then translate Y, which was the second one. So basically the data class is intelligent about it, and it is able to rechange the order or change the order in which those things need to be defined. And that's because Python has that as a requirement. Well, this gets us to how we can create data classes programmatically. Right now, the way we create a data class is we write a class and then we decorate it. Sometimes we want to be able to create a data class by running another piece of code, because maybe we have variables that are going to be used to define all these different things inside of here. So we don't have static code that's being used to generate a class. We have dynamic code that's being used to generate a class. And the data class module gives us that possibility as well. So let's take a look at this class. Let's just put it back here so it's clean. So I have it in the order that I want. Keyword only, already both listed here in the correct order. Not that it matters, since the data class will reorder it for us. And what I'm going to do is I'm going to say from data classes, I'm going to import make data class. And I'm not going to spend much time on this. There's not really a whole lot going on with it, but I'm just going to show you what I mean by programmatically making a data class. I'm next going to define a function. So this is just going to be a function which is called post-init. It's going to take 3 positional variables, one called self. I don't have to call it self, I could call it something else, but I'm going to call it self because it's going to end up being a method in a class. So that first one is usually called self. And then it's going to take translate X, translate Y. So basically I'm taking this over here and I'm defining it externally, right? I'm just doing that in my module. And then what I'm going to do is I'm going to create the same data class that we have over here, the same one. I'm going to create this way. I'm going to call the make data class function. If you've done name tuples before from the collections object, from the collections module, you know exactly what we're doing, right? We're creating a data class programmatically, just like we would be creating a name tuple programmatically. You have a more declarative style with the named tuple in the typing class. But if you want the programmatic style, you have it in the collections module. So the same thing's happening here. So this is going to be the name of my class. Happens to be called the same, but this name doesn't have to correspond to this one. And then I'm giving it the fields as a list. And I'm saying, here's the name of the field. Here's the type of the field. Here's the default value for the field. Here's the name of the field. Here's the type of the field. Here's the default value for the field, which is a field instance now. With default of 0, keyword only is true. And then we specify order equals true. And then we have this namespace. So this namespace is where I can give it extra stuff that I want to put into this new class that I'm creating, the circle D2 class that I'm creating. And I want to give it an entry in this dictionary saying I want something called dunder post-init, which is going to point to this function over here, post-init. So if you're wondering about this namespace, it's very similar to the dict argument in the type function when we use the type function to create new classes. I'm not going to cover this here because I do have it covered in the deep dive course series in part 4, and in this notebook I have a link to the deep dive series repo on GitHub, which is completely free, where you have basically all that information in there about types and namespaces and things like that if you're interested in that. So now we can say C equals circle D2. We don't have to pass it anything. And then, we see this translating center. That's coming from this over here. Didn't do any translation. We have the wrapper. Everything works just as if we had defined it completely declaratively this way over here. It's identical. Okay, so the next topic that I want to look at is custom metadata and how we can add custom metadata to the fields in a data class. Now, currently, I don't know of anything in Python or the standard library that actually uses this metadata for anything. There are certainly third-party libraries out there that do, and you may have also a use for it. I mean, for example, we might have this person class. So let's go back. Let's just create our person class this way. Let's say we've got this person class and we want to add information about each field. And we want to add how the field in this class maybe maps to a table and column in a database. And we could certainly maintain that information in a dictionary somewhere, but the data class already has this fields, right, introspection. So it would be nice if we could add this directly into this field over here. We can see that we have other things as well, like init equals true, wrapper equals true, hash equals none. Hopefully you're starting to understand what these things are, right? That's how we were able to define and refine how the data class was getting created. So it would be nice if we could just add the metadata. And look at this here. We have this metadata property, and it's a mapping proxy, which you should know is basically a immutable dictionary, a mapping proxy. And we can easily basically specify what the values should be for this metadata. And all we need to do is to go in here and just type metadata equals, and then we provided a dictionary. Or you could also provide it a mapping proxy, I guess, but you can also just provide it just a dictionary. So let me add that in for each one of them. So we'll say that was the person, column was name, person, column is current age, and let's say here, now here I've got strings, so what I'm going to say is now I need to create a default value. It's going to be a field, and we'll say the metadata equals that. I don't need anything else in that field. So now when I do this, you'll notice that now my metadata has been populated. And of course, I can read that back. Now, as I said, Python doesn't use it. Even if I do a help, let's say on person, you'll see that even though I get a few things in here, right, like the type hints are there and so on, you'll notice that it doesn't give me any information about those fields, right? So let's just go through. You can see it really doesn't give me anything. So that metadata doesn't actually get used anywhere, but you can access it, right? We saw, so if we look at fields, person, that was a list of fields. We can look at the first field, and then we could look at the metadata property. So metadata. Okay, and we get that person, column name, etc. Okay, so that's metadata. Now, an important thing to talk about as well is how to initialize fields with mutable objects. This is a common issue that many Python beginners make, and even sometimes not even beginners, is when they're initializing something like, a mutable, type, like for example, a list, and they might do something this way. And I have that in the notebook, and I'm not going to repeat it here because if you already know, there's no point in me wasting time. If you don't, you can just read it. It's straightforward. But you should never do something like this. This is going to create endless problems. Let me show you. I can go ahead and say numbers. You might think, right, that if I call squares and I don't specify L, it's going to create an empty list. It's going to append it to that list and return it. And if you look at what numbers is, it's like, yeah, it's exactly what it did. Great. So now let me do this again. So now I'm going to say others equals squares and 2. So what do I expect here? Well, it's going to call squares. I'm not passing L. It's going to create a new instance of the list. It's going to or it's going to create an empty list. It's going to append this to it and then return that list. And what do I get? Well, I get something strange. My others has the 1, 1 from the other call, right? And this is very typical for beginners to fall into that trap in Python. What happens is that when does this thing get created? Well, it gets created when the function is created, not when the function is called. So by the time I've executed this piece of code, that list default has already been created and it's been stored with the squares function. So now when I call squares 1, I don't pass L. The squares 1 is going to retrieve this list that's stored with itself as the default. And it's going to append to it. When I call squares again I don't pass this L. It's going to go back and grab that same list, that same object that's stored with it, right, with the squares function. It's going to grab that and it's going to therefore append to it. And now we've got therefore the result here from the previous call and the result from the current call. So we don't want to do it this way, right? What we really want to do is maybe do something like this. We will say L equals none and then inside the body of the function. So now we're moving, creating this empty list out of the defaults, which is something that happens only once when the function is compiled, to inside the function, which happens every time the function is called. So I'm going to say if L is none, then L equals new list, right? So we'll do it this way. Now this will work just as before, but now when we call this one, well, we get the correct result because remember, this list is getting created only when we call squares. So it's getting recreated every time. All right, and then the same thing happens, of course, with methods in classes too, like in the init. If we want the init to have a default for an argument that's going to be a mutable default, that can lead to problems in the same way because the init is going to have argument equals, if you put argument, let's say L equals the parentheses, the square brackets that we had before like that, that's going to be a problem. Whether it's on a function or in a method, doesn't matter. So the same thing is going to happen with data classes. What if we want to have a data class which has a default that's a mutable value for one of the fields? So we can try doing this, right? So what I mean is this. Let's say that we have this class test and we want to make it into a data class, and I want this tests to be a list, and I want it to have a default of an empty list. And then I'm putting a method on this class that's going to append something to that list. So that's what I want to do, and I don't want to have to specify this in my init, which is why I'm providing the default, right? This is the only field in my class, and I want it to default to an empty list. So if I try and run this, you'll notice that the data class decorator raises an exception. Says, no, this is a mutable default for the field tests is not allowed. And that's because basically data classes is trying to stop you from making that mistake. Now, the way that data classes tries to identify if something is mutable, how does it know that this is mutable? I think the more recent versions, they approximate that with the hashability. So they look at whatever you specify here. Is that a hashable object? If it is, that means that it's probably immutable, and that's okay. But if it's not hashable, it's probably mutable, that's not okay. So it's not a perfect thing, but that's the way it tries to do it. So as developers, we just have to be aware of this and to be careful about what we specify here. Data classes will try and catch it, but it can't always do it, 100%. So how do we do this? Well, if we look at an equivalent thing that we might have, let's say with a custom class. So instead of doing a data class, let me go ahead and do a custom class. And we're going to do basically what the data class does, or the way we want the data class to work. So I'm going to have an init. My tests is going to be none. And inside the init, that's the correct way of doing it, I'm going to check to see, well, if tests wasn't passed, if it was none, it wasn't passed in, make it into an empty list. Otherwise, just use whatever was passed in. I'm assuming that you're going to pass a list in. And then write this method that's just going to append to that list. Okay, so we have that. So if we write test like so, and we don't pass anything, we're fine. We can say t.add 1, we can say t.add 2, and then we can look at t.tests. That works just fine. If we say t2 equals test, we do another instance, we're not going to have a problem because every instance is going to have its own list, right? Its own instance of tests over here. So that works just fine. And works just fine if I actually use t2, okay, like so. So it works just fine, right? We don't have the 1124 that we had before. So this would be one way of doing it, right, with a custom class. Another way that we could do it is by using this concept of a factory function for tests. So what I'm going to do is I'm going to rewrite it this way. And it's basically the same thing, but for tests, I'm going to specify that I want a test factory, and that should be a function. I haven't typed hinted, but that should be a function. And what I'm going to do is I'm going to create this tests, right? Instead of just saying, hey, it's equal to this empty list, I'm just going to call this factory function, and it's going to return an object, whatever it is, and that object should just support the append. And of course, you'll notice that because it's happening in the code of the init, it's not happening as the default, right? So again, we're not having that other problem that we had. And so we pass in that factory. So how do we use that? Okay, but that's the basic idea. Well, we'd say t1 equals test. And well, let me write a factory function. Let's say def factory func, and it's not going to take any arguments, and it's going to return, let's say, an empty list. Or I could have a list that's pre-populated with something, right? Doesn't really matter. Here I'll just return an empty list. And now I'll say t1 equals test factory func, and then we'll say t1.add 1, and then we'll say t1.tests. Okay, so that works as expected because what happened? Well, factory func is going to return an empty list. Well, that's what happens here. Self.test gets, basically an empty list here. Then we added 1, it added that to the list. And if we do the same thing now using t2 with another instance of test, of course, we're not going to have an issue because we're dealing with two different instances, right, of a list. Every time we're calling the factory function. Every time we create a new test instance, we're calling init, and inside the init, we're creating this new empty list. So we're safe. So that's what I mean by a factory function. Now this, of course, is kind of silly because instead of just calling that, which in turn just creates an empty list, we can do the same thing by just saying list. Okay, so that's just another way of doing exactly the same thing. List is a function, right? Or list can be used as a function call. It's a callable, I should say. And so it's fine to use as a factory function. And so that's exactly how data classes implement this as well. So we can go ahead and do this. And for my default factory, I'm just going to use a list. So the way we do that is we again use this field, and then field has a attribute or a parameter, an argument called default factory. And we can just basically pass the factory function that we want. So here we can just pass list as the factory. So if we do this, we can now say t1 equals test. Okay, just like before. We can say t1.add 1. So now we're going to call that method. And then we can say t1.tests. And we can look at that. That's correct. Now if we do another one, t2 equals test. And then we say t2.add, let's say 2. And if we look at t2.tests, you can see that that's correct, and t1.tests is still correct as well. So that is how data classes do it. They use this default factory Took a while to explain, but this is essentially what it's doing over here. All right, so this was another long video. So in conclusion, you can see how data classes can save us a lot of typing. But, of course, data classes have limitations. They're not replacements for Python classes. The data class decorator is a code generator that essentially generates the code required to add functionality to a class, just as if we had typed it ourselves. This means that not every possible eventuality can be covered by data classes, right? There's going to be times where you just don't have what you need that you want to implement in a custom class available via data classes. Obvious things are things like context managers, or maybe the iterable or the iterator protocols. You wouldn't think of using a data class for that, right? So there's going to be a certain point where the data class is just not going to work for you. Now, when this happens, don't fight it. Don't fight this code generator and try and work, writing all kinds of weird workarounds. Just switch to writing standard classes. And this is why I said right in the beginning of these videos on data classes that it's important for you to understand how to build classes by hand before you start using data classes. Because data classes are opaque. So when you run into these limitations, you'll know exactly why you're running into them. Hopefully, you will know how and why you're running into them, with data classes. And you'll also have the knowledge of, okay, well, since I can't use a data class, how do I do it from scratch? Now, also don't forget the attrs library. It is a superset of data classes, and it may very well have the extra functionality that you need and still then not require you to write, a lot of boilerplate code by hand. Maybe the attrs has sufficient extra functionality that you don't need to write custom classes completely by yourself. You're still not going to use attrs for things like context managers and so on. At least I wouldn't. So personally, I use data classes for simple and straightforward classes that really are about data structures, right? About data fields, where that's the main goal of the class. So I also have a link back to the PEP in this conclusion in the corresponding notebook that's in the GitHub repo. But you should read that and take a look at the reasons for why data classes were created and the rationale for them. That's in PEP 557, so there's a link to it there. And that's it for data classes. I hope you enjoyed this 2-part series. Thanks for watching.